Okay, welcome to statistics. This is Thursday, 5/14. Today we're going to do inference about two means, independent samples. And this is a problem we saw earlier in the year, if you remember. 14 male rats were sent up into space. Upon their return, their red blood cell mass in millimeters was measured. A control group on Earth received the same conditions as the rats in space with the exception of space travel. The data on the next screen shows the red blood cell mass of both groups of male rats. Does the evidence suggest that the flight rats have a different red blood cell mass than the control rats at the alpha equaling 0.05 level of significance? And yes, this was an actual test by NASA. You want to kind of right away say, because we're wondering if it's different, it's going to be something that's not equal, right? Or it's going to be a two-tailed test. It's not like it's less than only or greater than only. It can be either one. So that becomes a two-tailed test, and the idea is being not equal. By the way, when I said we saw this, we're now applying this question to a different problem here, of course. But we will assume that this data comes from a population that is approximately normal with no outliers. Yesterday in the lesson, we did one where we didn't assume that, and we ran a little test on it. And we want to know if the flight rats, the ones in space, have a different red blood cell mass than the non-flight, the Earth rats. Therefore, we need to consider each group's mean or average red blood cell count. These are all the counts of the one they had in space and the red blood cell count with the ones on Earth. Copy that down. I'll pause the video, please. All right, so like I said, we're testing to see, are they equal? Are the red blood cell counts, the averages, are they equal or are they simply not equal? Are they different? Clear all the memory in your TI at this time. And what you're going to do is you're going to enter all of this, the space ones, in list 1. So go to your stat key, go to edit, hit enter, and you see L1 and L2. Put all of the Earth data in L2. Now, once you get all that put in, you're going to go to calculate one variable stats, and you'll see list in there, and list should probably come up L1. Well, that'll be all the information to get the mean and sample standard deviation for list 1, the space rats, okay? But then you're going to have to do it again and change list to L2, and that's a second function number 2, okay? On your calculator, second function number 2, there's a little L2 right above there. And that'll give you the mean and sample standard deviations for the Earth rats. All right, pause the video and see if you can get those right now, the mean and sample standard deviation for both groups. Okay, if you didn't get these answers down here, email me. All right, if you didn't get those down there, email me. Now for your notes, pause the video and write that down. So what is Welch's approximate T? Okay, it's that right there. It's a new formula, okay? And this S1 with a 2, it means the sample size of the first group to the second power. The sample size of the second group to the second power. I couldn't get little numbers to come in, so that's the best way I could do it with technology. All right. And it says up here, by the way, when the population means and standard deviations are unknown, why would the population mean be unknown? Because we've never sent all rats into space, okay, the entire population of rats into space with these conditions. And, we couldn't. So it's unknown. All we can rely on is samples here. So when that's the case, we're using Welch's approximation or approximate T. Now, both means in this formula, M1 and M2, are 0. because we're assuming a normal distribution curve. So if it's a normal distribution curve, we can say, well, right in the center can be a mean of 0, and then we go that many that way and that many that way. So we can just say M1 minus M2 is just nothing. It's just 0 minus 0. All right. So if you take all of this information, put it down in here, you should get your t value of negative 1.437. Pause the video, see if you get that. If you didn't, email me. All right. Now we're going to determine the critical value at the alpha equaling 0.05 divided by 2 level. All right, let me jump right here. You have to divide the alpha in half because we're considering equal versus not equal. In other words, the picture is looking like this. See, it's this way and this way. So it's dividing the 0.05 up 2 ways. All right. Back up here. Determine the critical value at the alpha equaling 0.05 divided by 2 level of significance with 13 degrees of freedom. Why? Because the sample size was 14. So 14 minus 1. Go to table 7. I know I've done this several times, but hopefully it's becoming old hat for you now. Table 7. And on table 7, run your finger down to 13. And you're looking for 0.025. Because that's 0.05 divided by 2. So 13, 0.025 is right there. Run your finger along 13, come to 0.025 where they match up, 2.160. You can also use inverse t in your calculator with 1 minus 0.025. Both should give you 2.160. Now, this is a two-tailed test. So we're not only using down here the positive 2.160, but the negative, okay? All of the area that way, all of the area that way. Well, notice your 1.437 from the previous page, it was actually negative, but again, it's negative. We're going to use the positive as well. Neither of those fall into the critical region. The test statistic does not lie in the critical regions. Do not reject the null. We would say then that the averages are equal. Okay. What is the p-value for this test hypothesis? To determine the p-value, find the area under the curve corresponding to 1.437. The t-statistic lies between 1.350 and 1.77 when using 13 degrees of freedom. Table 7 again, go to 13 degrees of freedom. You're looking for 1.437. There's no negative 1.437, so we just deal with the positive. But walking my finger along here, I see 1.350 and 1.771. That's where 1.437 lies between. Go up to the top, and you see they correspond to 0.10 and 0.05. Okay, so the area under the curve for 1.437 is between 10% and 5%. We double these amounts because we have a two-tailed hypothesis, making our areas 20% and 10%. The p-value is between these amounts, okay? Like I wrote here, not to scale, but the areas to the left and right of these line segments make up 10% and 5% of the area under the curve. Right there is your 1.350. All of that area past 1.350 is 10%. Right there is your 1.771. All of that area to the right of that is 5%. So, okay, same with on the negatives on the other side. Well, the 1.437 is in between 10% and 5%. But we, right here, 10% and 5%. But we double them, so now we're saying our p-value is between 10 and 20. All right. Keep the null hypothesis because a probability between 10 and 20% is reasonable if indeed the hypothesis is true. All right, we're going to do that same problem now using stat. So turn your calculator on, hit stat, go over to tests, scroll down to number 4, 2 sample t-test, hit enter, okay, and highlight data because you're using all the data in your lists that you put in earlier with the red blood cell counts, okay. And for list 1, L1, list 2, L2, those should be in there automatically. If they're not, you got to change them. Frequency 1 and frequency 2 should both be 1. Keep those the same. Change them if they're not. Highlight not equal to M2. Hit enter. Highlight no for the word pooled. We'll talk about that later. And then you got to hit scroll down to get the word calculate to come up. All right. But calculate comes up when you scroll down. Hit enter on calculate. And here's all the information. Is your t statistic showing negative 1.437? It should be. Is your p-value 0.16? Okay, and is this between 10 and 20 like we said? Yes, it is. Okay. Is your mean differences and standard deviations the same as what you got earlier? Okay, you can scroll down a little bit more to get the standard deviations, but I'm looking at them. They're the same as what we had before. And on a final note, since the p-value is 0.16, 0.16 is greater than the alpha, we do not reject the null hypothesis. Remember the other problems we were doing? They were always less, so we were rejecting. Now it's not less than 0.05, okay? So we're keeping it. Notice that DF in your calculator, okay, is showing up as 25.996 instead of 13, okay? That's on that screen for the sample, two-sample t-test. For your notes, copy that down. Okay, so in your notes there, you realize that the computers are using a different formula for the degrees of freedom, allowing for an increased precision in determining the p-values. All right. Don't worry about knowing this formula, but it's on page 495 if you're curious. Now we're going to construct a 95% confidence interval for the difference in the two means of the rat's red blood cell count. Okay. You have all the information here to use this new formula, okay? Remember, that's S1 to the second power. That's S2 to the second power. It's under a square root, divided by the N1 and N2. The only thing you don't have is the T alpha 2, alpha divided by 2, I should say. Well, a 95% confidence interval implies an alpha value of 0.05. Use table 7 to determine T sub of alpha divided by 2 with 13 degrees of freedom. Alpha divided by 2, therefore, would be 0.025. So once again, run your finger down to 13, find 0.025. 13 and 0.025 match up at 2.160. You could also use inverse T with 1 minus 0.025, degrees of freedom 13. Both give you 2.160. So let's write that in. T alpha divided by 2 is 2.160. That number is going to go right there. Work all that out. One of them you add, one of them you subtract. Okay, that should have that the other way around. Subtract there, but it still means the same thing. Okay, one of them you're adding, one of them you're subtracting. Pause the video, see what you get. Okay, did you get negative 1.374 and 0.276? If you didn't, email me. Going to use technology now to do that same problem. Let's hit the stat button. Okay, hit the stat, scroll to tests, scroll down to 0. Now 0 is after number 9. So you see 7, 8, 9, then 0. And 0 should be two sample interval. Hit enter. Okay, let me put a little arrow there just so I'm sure most of you know that. But after that point, hit enter. And you'll see some information here for input. Keep it data if it's not already. Or I should, yeah, if it is data, keep it that way. If it's not, then change it to data. List 1 should be L1, list 2, L2. Frequency 1 and frequency 2 should both say 1. The C level, our confidence level, was 0.95, so change it to 0.95 if it isn't already. For pooled, highlight no again. Scroll down, go to calculate, hit enter. All right, and at the top of the screen, you should see your interval. Now, is your interval slightly different? On the previous page, remember this down here? Our interval was negative 1.374 and 0.276. Your calculator now is saying this, okay? It's not that you did anything wrong, it's just why is that the case? It's the DF thing again. The DF is 25.996. Okay, so it has to do with how the calculator does it differently than doing it by hand. If I gave you an assessment on this, either one would be fine. Okay. All right. Copy that down for your notes. Pause the video. All right, so like we say on here, 95% of our samples, and I should insert in there, samples of 14 will have a difference that is as low as negative 1.355 and as high as 0.236. 0 is obviously in between those two numbers. So the interval sometimes even a 0 difference. Last thing to write down, you might see something like this on some homework problems, so just copy that down. Okay. And there's some homework problems to do. Have a good night.